Welcome to the Deep Dive, where we take the most complex research, stack up the sources, and extract the knowledge you need to be truly informed.
And today, we are opening the file on a paper that, really, it changed everything.
We're talking about the 2020 OpenAI paper, Language Models Are Few-Shot Learners.
This deep dive is for all of you, the students, the engineers, the just intensely curious minds out there trying to figure out how AI went from this lab curiosity to, well, to this general purpose tool that's everywhere now.
Yeah, seemingly overnight. And we're going to try and make this research really accessible. We're focusing on the big ideas, the intuition, not the deep math.
Exactly.
And you really can't talk about this paper, the GPT-3 paper, in a vacuum. You have to place it in context. I mean, if you just rewind a few years, you had the attention is all you need paper.
Yeah.
That gave us the transformer. That was the blueprint.
The fundamental architecture, right. That laid the foundation. And then you get models like BERT. And BERT proved this other critical idea. That you could take that architecture and just feed it massive amounts of text to pre-train it for general language understanding. BERT showed that scale was useful.
But this paper, the Few-Shot Learners paper, that's the real inflection point. It's the moment where scale stops just being useful and becomes the main innovation itself. It unlocks something new.
That is the critical distinction. I mean, before this paper, the prevailing wisdom, the paradigm was that no matter how big your pre-trained model was, if you wanted it to do a new task, say summarize a document or correct French grammar, you had to go through this whole painstaking process.
Which was called fine-tuning.
Fine-tuning.
Yeah.
And what did that involve?
It sounds expensive.
Incredibly resource-intensive. You had to go out and collect a brand new, large labeled data set just for that one task.
We're talking thousands of examples.
Thousands, sometimes hundreds of thousands of examples.
Yeah.
Then you had to retrain the model's weights using gradient updates to specialize it. Every new task was a new manual data collection effort. It was a huge bottleneck.
Okay, so the GPT-3 paper comes along and basically challenges that entire way of thinking with something they call in-context learning.
Right, which is where few-shot learning, or FSL, comes from.
So how does FSL get around that bottleneck?
It breaks it with one simple but non-negotiable rule. No gradient updates.
None at all.
None. The model's core knowledge, its weights, are frozen solid after that huge pre-training phase. All the adaptation happens just from reading the input text at the prompt. They call it the context window.
So you're basically teaching it on the fly, just with your instructions.
Exactly.
So let's define the 3 settings they explored for this.
Okay, so they defined 3 levels, and none of them involve changing the model's weights permanently.
The first one is zero shot.
Zero shot is the simplest.
Yeah.
You just give the model a natural language instruction. You literally just write, translate this sentence into French.
And it has to figure it out from that alone.
Entirely from its pre-trained knowledge and that instruction.
Okay, then you have one shot.
Which is the instruction plus one single example. It's like a little nudge, you know, a hint about the format you want.
And finally, the one that gave the paper its name, Few-Shot Learning.
Yeah, this is where they really focused their work. Few-shot is the instruction plus a handful of examples. Maybe 10, maybe 50, up to 100, all packed right into the prompt.
So into that 2048 token context window for GPT-3?
Right. Think of it like giving a super smart intern a memo with 5 examples of the tone you want, and then just saying, okay, go do that.
Now, this is where the scale thing becomes the big aha moment. Because when they tested this on models of different sizes, it wasn't like all of them could suddenly do this, right?
Absolutely not. And that is the punchline of the whole paper.
Okay.
They looked at models from, 125 million parameters all the way up to the huge 175 billion one. For the smaller model, say the 1.3 billion parameter one.
Which sounds big to me.
It sounds big, but in this world, it's not. For that model, giving it a few examples barely moved the needle. It couldn't really use the information effectively.
It wasn't smart enough.
Exactly. But the moment you jump to that 175 billion parameter model, the performance curve just shoots upward. It's a profound difference.
So the biggest models have much steeper in-context learning curves.
Dramatically steeper, meaning they absorb those few demonstrations so much more effectively and can just adapt to the task on the fly.
So scaling up didn't just make the model a little bit better at the old stuff. It caused this, qualitative leap. It unlocked a brand new capability.
Precisely. And that new ability meant that all of a sudden, Few-Shot GPT-3 was in direct competition with models that had been painstakingly fine-tuned for years.
Let's talk about that competition, because this is what made everyone in the field just stop and stare.
It really did.
GPT-3 comes in cold, just a few examples in a prompt, and it starts matching or even beating these highly specialized models.
It's the marvel of the paper.
Yeah.
Take something like Trivia QA. It's a really hard question answering benchmark.
Right.
Few-shot GPT-3 gets 71.2% accuracy.
Yeah.
Now, crucially, that was state-of-the-art for any model in a closed-book setting.
Meaning it wasn't cheating and looking up the answers on the web.
Exactly. It just knew it. The knowledge was embedded in its weights from tree training. And that's transformative.
The efficiency is just incredible. And you saw it on prediction tasks, too, like Lambda.
Oh, yeah, Lambda is a great example. The task is to predict the last word of a passage. It requires really understanding broad context.
So what happened there?
By just framing it as a simple fill-in-the-blank problem, in the few-shot setting, its accuracy jumped to 86.4%. That was an 18% improvement over the previous state-of-the-art.
Just from changing the prompt.
Just from the prompt. It shows that the framing of the problem became the tool for getting high performance.
Okay, let's get to the finding that, for me, was the most surprising. Arithmetic.
Yeah.
I mean, a language model is for words. It predicts the next token. Why would it be any good at math?
It shouldn't be, right? Math is about rules, not fluid text. And the smaller models were terrible at it.
But the big one.
The big one showed this just unbelievable emergent skill.
What were the numbers?
For two-digit addition, in the few-shot setting, the 175 billion model got 100% accuracy.
100%.
Perfect score. And 98.9% on two-digit subtraction. Even on tricky three-digit subtraction, it was still over 94% accurate. The jump from the 13 billion parameter model, which is basically guessing, to the 175 billion one is just, it's enormous.
Well, the first thing everyone thinks is memorization. It was trained on the whole internet. Maybe it just saw every math problem.
And that's the first thing the authors checked. They ran an analysis and found that a tiny, trivial fraction of the test problems were actually in the training data. For three-digit addition, it was something like 0.8%.
So it wasn't just looking up the answers.
It strongly suggested it wasn't.
So what was it doing? If not retrieval, it had to be trying to compute.
And that's what the errors suggest. When it failed, the mistakes weren't random. They looked like human errors.
Like what?
Like forgetting to carry the 1.
No way.
Yes. Errors like not carrying a 1 during addition. It suggests the model had somehow learned a kind of algorithm, a set of steps for doing math, and the few-shot prompt was just the key to unlock that algorithm.
It's not a calculator, but it learned how to pretend to be a really, really good one.
An amazingly good one.
Okay, so moving from computation to, I guess, creativity, the quality of the text it could generate, this was another one of those alarming milestones.
It really was. They ran these tests with news articles, about 500 words long, and they asked people to try and spot the difference between the human-written ones and the GPT-3 ones.
And I'm guessing people were pretty good at spotting the machine.
Barely. Human accuracy was hovering just above a coin flip, around 52%.
Wow.
And the key thing is, the bigger the model got, the harder it was for humans to tell the difference. At that 175 billion scale, we basically crossed a threshold.
A threshold where high-quality, long-form machine text becomes pretty much indistinguishable from ours.
Yep, and that immediately raises huge red flags about misinformation, spam, misuse.
The potential for misuse at scale.
Exactly. The ability to cheaply generate massive amounts of convincing, hard-to-detect disinformation. It moved from sci-fi to reality with this paper.
But it wasn't just about doing existing tasks well. It could also learn totally new things, right? I'm thinking of the synthetic tasks.
The synthetic tasks were maybe the most compelling proof of genuine adaptation. They tried teaching it things it could never have seen online.
Like what, for example?
Like word scrambling. They'd show it a few jumbled up words and the correct answer, and in the few-shot setting, it could then start unscrambling new words.
That's pretty impressive.
But even more impressive was learning nonsense words.
Wait, what do you mean? Give me an example.
Okay, so they would just invent a word, let's say gigamuru, and they defined it in the prompt. A gigamuru is a type of Japanese musical instrument.
Right.
Then they asked the model to use gigamuru in a new sentence. And it could. It could correctly use this brand new concept, showing it could rapidly internalize meaning and syntax for something that was completely absent from its training.
That's way beyond just pattern matching. That's adaptation.
It's rapid conceptual adaptation. It's a whole different level.
So this all sounds like an unstoppable superintelligence, but every system has its weaknesses. What did the authors say GPT-3 was bad at?
Oh, they identified several big ones. It proved that general intelligence was still a long way off. For one, it really struggled with common sense reasoning.
Particularly physics, right.
Basic physics, yeah. The authors noted informally that it would get tripped up by really simple questions.
Like what kind of simple question?
A question like, if I put cheese into the fridge, will it melt?
Which any person knows instantly.
Instantly. But the model, despite having read basically the entire internet, struggles to synthesize that kind of basic physical knowledge. It shows having all the facts doesn't equal common sense.
And it also struggled with certain comparison tasks.
Yeah, it was often near random chance on things like natural language inference, or NLI, which is about figuring out if one sentence implies another. It also had trouble with word in context, telling if a word is used the same way in two different sentences.
So its skills were more in generation and retrieval than in sharp logical deduction?
Exactly. The nuanced, subtle comparison tasks were a real weak spot.
Okay, and beyond performance, we have to talk about the data itself. 400 billion tokens from the internet means you're scraping up all the bad parts, too. The paper addresses bias head-on.
They had to. As they put it, internet-trained models have internet-scale biases, and their analysis was, well, it was stark.
What did they find on stereotypes?
Their analysis showed that 83% of occupations they tested were more likely to be associated with male identifiers, especially high-status jobs like legislator or banker.
And for female identifiers?
Highly associated with appearance words. Beautiful, gorgeous. It's a mirror reflecting the biases in the text we all create.
And they also looked at race and religion.
They did. And again, this is us reporting the paper's findings. Their sentiment analysis showed Black was consistently associated with lower sentiment scores.
And for religion.
When prompted with religious terms, they found that completions for Islam were associated with words like terrorism and violent at a much higher rate than for other religions. It's a really sobering reminder that these models don't just copy our biases. At scale, they can amplify them.
And finally, let's just touch on the cost. That 175 billion parameter model, that wasn't cheap to build.
Far from it. We're talking thousands of petaflops days of compute, a massive investment of energy and money that raised immediate questions about who can even build these things.
But the authors did make a counterpoint about efficiency once the model is actually trained and running.
Exactly. They stressed this idea of amortizing that huge upfront cost. Once it's built, running inference, actually using it, is relatively cheap.
So you train one massive generalist model.
Instead of dozens of smaller, specialized models that all need their own fine-tuning. That's the argument.
So if we pull all the way back, the real legacy here is that just pushing scale, making the model bigger, caused this emergent capability, few-shot learning, to just appear.
It appeared. And it completely changed the game. We went from a world of specialized AI experts to a single, hyper-competent generalist.
That's the shift.
That is the defining shift.
Yeah.
But the paper, for all its breakthroughs, left us with this huge, important question that we're still grappling with today.
Which is?
When GPT-3 does few-shot learning, is it actually learning a new task from scratch, right there in the moment?
Or is it just that it's seen so much data, so many patterns, that it's just recognizing a skill it already learned during pre-training?
And the few-shot prompt is just the perfect key to unlock an ability that was already there, dormant.
So is it de novo learning, or is it just hyper-efficient pattern recognition?
That tension. That's what defines the start of the large language model era. The black box got so much bigger, and figuring out what that scale truly unlocked is still the central mystery we're all trying to solve.